So now that we've got the velocity time graph, let's try to make the other graphs of motion. So I'll make the position time graph first. Now, how are we going to make this into a position time graph? Well, the first thing that we have to do would again be to deal with the area, because again, the area under the curve of a velocity time graph is simply the displacement, and those are the numbers that you need for position. Okay, so this entire area over here. Let's start with this one. Part A. I think I'll use this pencil instead. So this bit here is a triangle. Okay, it has a height of 9 meters per second, and it has a base of 15 seconds. And because it's a triangle, we have to divide all of that by 2. Okay, so if I'll just quickly get my calculator out, gives me an area of 67.5 meters. So this entire bit here has a displacement of positive, because it's in the positive, 67.5 meters. Okay, now let's go to segment B. So this time we have a rectangle. Okay, it still has a height of 9, however this time it has a base of 10. Okay, so 9 meters per second times 10. I think we don't need a calculator for that. We can simply say that 9 times 10 would be 90 meters per second, and this is in the positive direction. So 90 meters. Okay, not 90 meters per second, but 90 meters. Now this thing in part C is a little bit complicated. Okay, but one thing we could do, we could actually divide this into a rectangle and a triangle, as I'm going to demonstrate. Okay, so first let's solve for the area of 1, add it to the area of 2, then we have the total area of this entire region over here. Okay, so what's the area of 1? The area of 1 has a base of 30. It has a height of 6. Okay, so 30 times 6, we can do that. That's simply 180 meters. So this region over here is 180. How about area of 2? Well, this is a triangle, as you could see. So 1/2 base times height is what we need. What's the base? The base is simply still 30. 1/2. But the height, it's 9 to 6. Okay, 6 here, 9 here. 9 minus 6 is simply 3. Okay, so actually we could do this. 30 times 3 is 90, and divide by 2, this is 45. So therefore, the area of this entire thing is 1 plus 2, the two areas combined. Okay, so that's 180 plus 45, and that will lead you to 225 meters. Okay, so that entire thing here has an area of 225 meters. Actually, I solved it by means of rectangle plus triangle, but if you notice, you could actually solve it by area of a trapezoid as well. It should arrive at around the same mark. So positive, because it's above 0, 225 meters. And finally, for section D, it's a very small triangle over here. 10-meter base, height of 6 meters. So I think we can solve that. 10 times 6, that's 60. Divide by 2, that will give you 30 meters. So it's still in the positive because you're still going positively, but 30-meter slow down, and that is your displacement. Okay, so how about the position time graph? How are we supposed to do this? The values that we're going to use for position time are actually the ones that we calculated for. So the first bit is, because we traveled 67.5 meters forward in our acceleration phase, we simply put here 67.5. Okay, next phase, 90. So now we can get our calculator and actually add the 67.5 to the 90. This gives me 157.5. So that's going to be, the next phase of our graph, 157.5. Okay, what's the next bit that we solved? It's 225. So we now add 225 to the 157.5. So 225, to get 382.5. So let me go and just label that. It doesn't have to be proportional for this rate if it's not on the graphing paper. And finally, we just simply add 30 to the very end. So add 30, 30 gives me 412.5. Okay, so I'll just put a 412.5 over here. And those are the positions that our car experiences these changes in the way it moves. Okay, so now what's next? I now have to plot the points per second. Okay, so we know that segment A ends after 15 seconds and at 67.5. So that's for A. 25 will end at 157.5. That's for B. For C, it ends at 382.5, so I'll put it right around here. And for D, ends at 65 seconds, 412.5, so I'll put it right around there. So there's the plot. What is the shape of the graph going from the different points? Okay, this is when we get our motion graph know-how and try to translate what these are. Okay, this one, you're moving at a constantly accelerating speed. Okay, so that means that for every second you become faster and faster and faster. And when you go faster and faster and faster, this obviously means getting steeper and steeper and steeper. So again, steeper and steeper and steeper. I'm just exaggerating the curve so that you can have a visual representation. But anyway, that's what it's supposed to look like. This bit, you are going at a constant rate. Okay, but it's a positive velocity. Okay, so if you're going constantly but in a positive velocity, you're still moving forward, you can have just a simple straight line connecting these 2 points. Okay, that's the case of motion that is interpreted. How about this one? You are going to slow down a little bit. Okay, so when you are slowing down, you start off really, really steep, 9, and then you become a bit less steep at the end, 6. Okay, so I'll just exaggerate the curve. Start off really, really steep, and then you plateau and at a much lower rate. Okay, and finally, okay, you are now going to slow down. Okay, you're going to slow down to 65. So this one is actually the same case of motion, but it's going to be at a more drastic kind of rate. Okay, so something a bit like this. So that is your position time graph represented using the values as you could see.